Hello everybody, welcome back to the channel. Today we're going to talk about the network function and the responses. We're going to look at two types of responses. One is the impulse response, the other one is the step response. As always, I'm going to have the link to the Google Colab notes in the description down below. So if you have any comments, feel free to leave there and share your thoughts there. So let's look at so I'm going to have two topics. One is the network function and impulse response, and the other one is the network function and the step response. Fairly straightforward two topics, but I'm going to have three video clips. In the third video clip, I'm going to show on the breadboard here. I have this analog Discovery Studio. I'm going to show you the example we calculated. Actually, we can see on the scope. It's pretty cool. Stay tuned. And let's start with the first, the impulse response. So let's see the network function concept is that if we get the network function figured out, right? So let's see, we use that. We use TS. So this is the network function. And so the output is just the output, or we call it response also, and just the transfer function, the network function times the input transform, right? If the input is an impulse, so in that case, if the xt is delta t, or the xs would be equal. That's the Laplace transform of xt, which is probably the simplest one in the Laplace transform pairs, right? So this is just equal to 1. And in this case, we instead of using ys, we use hs. This is a fairly commonly used notation for the impulse response. So the hs is the ts times xs, which is equal ts times 1, right? Because in this case, the input is the delta function, or the input transform is just 1. So the response in time domain, the ht is going to be equal to the inverse Laplace transform of hs, right? And that's going to be equal to the inverse Laplace transform of ts. So therefore, all the poles, remember all the poles, let's see, if the TS has simple poles, in that case, TS maybe can be written in the form of the partial fraction expansion, let's say Kj over S minus Pj, J maybe from 1 to n, depending on the number of poles you have. And in this case, the inverse Laplace transform of this is going to be equal the summation of I use j, ki. I think it should, doesn't really matter that much. Let's see, use kj, so kj times e to the power of pj t, right? So in this case, you see the impulse response, although the delta function is very abstract, right? The impulse has infinite the amplitude, but also they have the width of 0. So I mean infinitely close to 0. But the impulse response has important information, right? So that's the one thing we want to keep in mind. So therefore, the impulse response is very important because it contains the information of the system. Remember, the TS, although TS is defined by as a ratio of the output over the input transform, but the TS is determined by the network itself. Basically, what are the elements are, or the characteristics of each element, and also how they are connected. That's what they basically the underlying network. But so the HT is sometimes very useful in term modeling because it contains all this information. If you can get HT and you can do the Laplace transform and find out the TS. That's very interesting, right? So let's look at an example. This is a simple example saying I have this circuit, I have a RLC. So in this case, I have the inductance impedance 5S and the capacity impedance 2/S and 2 ohm resistance. And I would like to find the I2T if the V1T is a delta function or the impulse. So in this case, I would like to start with the transfer function of Ty. So this is a kind of two-pole network, right? So we have Ty as that's equal I sub 2 over V1S. So if I can find this one and the impulse response I2T, and that should be just equal to the inverse Laplace transform of the T, right? So that's where I'm going. So in this case, let's see if we can, it's not straightforward to see the relation between these two, and let's just do as solve this circuit. So let's see, reform this as given V1S, try to find I2S, and then I take the ratio once I find the I2 in terms V sub 1, right? The quick way of finding this is I just do the source transformation. In this case, I have the 3 impedance in parallel, right? And the source here would be V1S over 5S. So this is 2 I2S. So this is the current division now. So this is 2 over S, and this is 5S. So I have the current division. In this case, the current division I sub 2S is just equal to 1 over 2, right, divided by 1 over 2 plus 1 over 2 over S. So I'm just doing the S over 2 plus 1 over 5S times the total current, which is the V1S divided by 5S, right? So that's the current division. I hope that's correct. Let's see if we work out this the math. So I have a 2. So let's just do it in 2 steps. So I have 1 plus S plus 2 over 5S. So now I multiply 5S, then times V1 over S, right? And so therefore we can see this going to be equal to 1 over 5S squared plus 5S plus 2, that's equal, that's plus, that times V1S. So therefore Ty is equal to, is V1, is I2 over V1. I2 is the output over V1S, and times, that's equal to, I'm gonna write this slightly different. So that's a 0.2 over S squared. I want to have the coefficient in front of S squared as 1. So I have plus S plus 0.4, right? So this is the Ty, and trying to find the I2, and I2T is just the inverse Laplace transform of Ty. And in this case, the Ty, this is second order, right? Let's see if we can, this looks like it has a complex poles, right? So in this case, we only have one term. We can change the form so that we can use the Laplace transform pairs. The form I want to change here is rewrite Ty as 0.2 over, let's see, S plus 0.5 squared. In this case, this will give me s squared plus 2 times 0.5, give me s, and plus 0.25, right? So, and in that case, I got minus 0.25, so I got 0.15 left. So what I did here is, let's maybe do this. Minus 0.25 plus 0.4, that's equal 0.2 over ss plus 0.5 square plus 0.15, right? And so here we have recognize this as alpha and this as beta square. So in this case, or as omega square. So that's the frequency. So in this case, we rewrite this as 0.2 over s plus 0.5 square plus square root 0.015 square. And in this case, we have the Laplace transform pair of omega over s plus alpha square plus omega square. This, the inverse Laplace transform of this one here is the Laplace transform. We have e2 minus alpha t, right, plot times sine omega t. So try to utilize these, and I would like to have this omega on the numerator, so I want to have the square root 0.05 pi to 0.15 on the numerator, so I need to divide that by s plus 0.5 square plus the square root of 0.15 square, and now I need to divide that 0.2, I still have 0.2 there. I need to divide this square root 0.15, right? So this is the form I'm gonna, now I can utilize this to get the inverse Laplace transform. Therefore, the I2 t is equal to the 0.2 over square root of 0.15 times e2 minus alpha t 0.5 t times sine omega t. Omega in this case is square root 0.15 t times the ut, and this in amps. In numbers, we call the numbers I calculated before, so that's, this should be 0.16 times e2 minus 0.5 t and times sine, and this square root 0.15 is 0.387, very low frequency, times the ut. And this example also fully worked out in the Google Colab. And this is the numbers, we got all the same numbers, and also there's Python code calculate the inverse Laplace transform for I2, and also I plotted this waveform. So this is the waveform of I2. It basically will have the impulse response, right? Since this is second order system, you can slightly see this. This actually the current goes to negative here. A little bit of oscillation going on there, right? So which is typical for a second order system because we have the capacitor and the inductance. And that's for this example. And we're gonna look at the step response in a moment, okay?